Hello everybody. In this video, we're going to study Wronskian determinant. We use Wronskian determinant to test whether the functions are linearly independent or not. If the Wronskian equals to 0, then our functions are dependent. If the Wronskian is not equal to 0, then our functions are linearly independent. If we are testing two functions, then we set 2 by 2 matrix. The first row will be y1, y2, which is our first function and the second function we are testing. And the second row will be the derivatives of the first row. If we're testing out three functions, then our first row will be y1, y2, y3. Our second row will be the first derivatives of the functions. And our third row will be the second derivative of the functions. And we take the determinant of this matrix and check whether it is equal to 0 or not. Let's see how we take determinant. So let's remember from our linear algebra class. If we have 2 by 2 matrix, then A entry times D entry minus C entry times B entry will give us the determinant. If we have 3 by 3 matrix, then what we're going to do is like this. First, we take the entry A, make a horizontal line and vertical line. Whatever left over is our 2 by 2 matrix. So A times determinant of this 2 by 2 matrix is our first part of the equation. Minus sign and plus sign we alternate. And as the second part of our equation, we take the entry B, make horizontal line and vertical line from B, and whatever left over is our 2 by 2 matrix. So we combine this. And B times the determinant of that 2 by 2 matrix plus entry C, make horizontal and vertical line, so you don't have to memorize. The leftover is your 2 by 2 matrix, and C entry times that 2 by 2 matrix's determinant will be your total equation. So this is how we take the determinant of 3 by 3 matrix. And from here, we know how to compute the determinant of 2 by 2 matrix. So determinant of this matrix is E times I minus H times F. And determinant of this matrix is D times I minus G times F. And determinant of this matrix is D times H minus G times E. And we have to multiply this by A minus we have to multiply this by B, and we have to multiply this by C. So the answer of this will be our determinant. In this video, we are going to do these 7 examples. We are going to compute the Wronskian of 2 functions, and on the example 6 and 7, 3 functions. Let's begin. First, we have e to the 2t and e to the negative 3t over 2. So let e to the 2t be our y1 and e to the negative 3 over 2t be our y2. So our Wronskian will be given by y1, y2, y1 prime, y2 prime. So y1 is e to the 2t and y2 is e to the negative 3 over 2t. The derivative of e to the 2t is 2e to the 2t. We bring the coefficient in front and keep e to the 2t. Similarly, the derivative of this will be negative 3 over 2 e to the negative 3 over 2t. And our determinant will be given by the multiplication of these two entries minus these two entries. So e to the 2t times negative 3 over 2 e to the negative 3 over 2t minus 2e to the 2t times e to the negative 3 over 2t. Here, if we multiply these two functions, then we obtain negative 3 over 2 e to the 2 minus 3 over 2 is 1/2 and t. Minus, if we multiply these two, we obtain 2 e to the 2t minus 3 over 2t is 1/2 t. So we have the like terms, so we can combine the coefficients. Negative 3 over 2 minus 2 is negative 7 over 2, and we have e to the 1/2 t. So this is our answer as our determinant. So the Wronskian is not equal to 0, so those functions are linearly independent. Let's go to example 2. Example 2 is cosine t and sine t. So our y1 is cosine t and our y2 is sine t. So our Wronskian y1 comma y2 will be given by this matrix: cosine t, sine t, and derivatives of cosine t and sine t. So the practical way to find the derivatives of trigonometric functions is this. So make a unit circle. Let this part be cosine. So this is going to be negative sine direction, negative cosine direction, and positive sine direction. Because this is x-axis and x coordinate of any point is cosine and y coordinate of any point is sine, so you can remember sine and cosine will be in those directions. If you go to clockwise, you get the derivatives of the trigonometric functions. If you go to anti-clockwise, then you get the anti-derivatives of the functions. And anti-derivatives are the integrals. So we're interested in derivatives now. So derivative of cosine is negative sine, and derivative of sine is cosine. Now we're going to determine the determinant by cosine t times cosine t minus negative sine t times sine t. So cosine t times cosine t is cosine squared of t minus negative sine t times sine t is negative sine squared of t. And this is going to be cosine squared of t plus sine squared of t. We remember this from Pythagorean identity, that is equal to 1. So our answer is 1, our Wronskian is 1, and 1 is not equal to 0, so our functions are linearly independent. Let's check out example 3. This time, we're computing e to the negative 2t and t e to the negative 2t. So the Wronskian of those two functions will be e to the negative 2t, t e to the negative 2t, and their derivatives. Derivative of e to the negative 2t is negative 2 e to the negative 2t, and derivative of this function is the product rule. So our t is f, our e to the negative 2t is our g, and the product rule is f prime times g plus f times g prime. So f prime is derivative of t, which is 1, and g is e to the negative 2t, plus f is t, and g prime is the derivative of this, which is negative 2 e to the negative 2t. So if we simplify, we obtain e to the negative 2t plus, let's use negative sign, negative 2t e to the negative 2t, because positive times negative will be negative here. So the derivative here will be e to the negative 2t minus 2t e to the negative 2t. Now the determinant will be given by this entry times this entry minus this entry times this entry. So e to the negative 2t times e to the negative 2t, negative 2t e to the negative 2t, minus negative 2 e to the negative 2t times t e to the negative 2t. And if you carefully multiply out, you're going to obtain, this is going to be e to the negative 4t, we combine the powers, minus 2t e to the negative 4t. Negative times negative is positive, and 2 times t is 2t, and e to the 2t times e to the 2t will be e to the negative 4t. So these two are exactly the same term with positive and negative sign. So the answer is e to the negative 4t, which is not equal to 0. So our functions are linearly independent. Let's go to example 4. On example 4, we have e to the t sine t and e to the t cosine t. Now our matrix will be this: e to the t sine t, e to the t cosine t, and their derivatives. So the derivative of e to the t sine t is the product rule. So e to the t sine t, let e to the t be f and sine t be g. So product rule suggests f prime times g plus f times g prime. So derivative of f is e to the t and g is sine t, plus f is e to the t and derivative of sine t is cosine t. So this is our next entry: e to the t sine t plus e to the t cosine t. If you would like, you can factor out e to the t, so you can write that as e to the t sine t plus cosine t, if that's going to be helpful. And our next entry will be the derivative of e to the t cosine t. So here our f is e to the t and our g is cosine t. Again, product rule is f prime times g plus f times g prime. So f prime is e to the t times g, which is cosine t, plus f is e to the t and derivative of cosine t is negative sine t. So we can pull negative sign to the front. And if you would like, you can again factor out e to the t and write it as cosine t minus sine t. Because we have written this in that form, let's use that form. So whichever form you're using, use two of them are the same. Now our determinant will be given by the multiplication of these two entries minus the multiplication of these two entries. So from the first multiplication, we have e to the t sine t times e to the t cosine t minus e to the t sine t, minus, from the second one, we have e to the t cosine t times e to the t sine t plus e to the t cosine t. Now we're going to distribute this inside. So e to the t times e to the t is e to the 2t. We combine the powers. And sine t times cosine t is sine t cosine t. Minus, again, e to the t times e to the t is e to the 2t. And sine t times sine t is sine squared of t. Minus e to the t times e to the t is e to the 2t. And cosine t times sine t is sine t cosine t. And finally, e to the t times e to the t is e to the 2t, and cosine t times cosine t is cosine squared of t. Now we can simplify negative e to the 2t sine t cosine t and positive e to the 2t sine t cosine t. Now we are left with negative e to the 2t times sine squared of t plus cosine squared of t. And we know this from Pythagorean identity. This is equal to 1, and 1 times this will be equal to negative e to the 2t. So this is our Wronskian. And we see that this is not equal to 0, so our functions are linearly independent. Let's go to example 5. Our example 5 is cosine squared theta and 1 plus cosine of 2 theta. So our Wronskian will be equal to cosine squared theta, 1 plus cosine of 2 theta as our first row in the matrix. And the second row will be the derivatives of those two functions. So derivative of cosine squared of theta will be the chain rule. We bring the power to the front, then we obtain 2 cosine theta times the derivative of inside function, which is cosine theta. So derivative of cosine theta is negative sine theta. And we have negative 2 sine theta cosine theta. Negative 2 sine theta cosine theta, here is the double angle identity, is the sine 2 theta. So we have negative 2 sine 2 theta. So here we applied the double angle identity for sine 2 theta. So now we're going to write here negative 2 sine of 2 theta as our derivative of the cosine squared theta. Now we're going to compute the derivative of 1 plus cosine of 2 theta. So 1 plus cosine of 2 theta. Derivative of 1 is 0. Here we're going to apply the chain rule. Derivative of cosine of 2 theta is negative sine of 2 theta times the derivative of inside function. Derivative of 2 theta is 2. So if we simplify, negative 2 sine 2 theta. So our second entry here is again negative 2 sine of 2 theta. Now we're going to compute the determinant. So determinant will be given by multiplication of these two entries minus multiplication of these two entries. Cosine squared theta times negative 2 sine 2 theta will be equal to negative 2 cosine squared theta sine of 2 theta. We have minus negative 2 sine 2 theta times 1 is negative 2 sine 2 theta minus 2 times sine 2 theta cosine 2 theta will be negative 2 sine 2 theta cosine 2 theta. You can compact this as double angle identity. It will be 2 sine 4 theta and negative times negative is positive. You can apply all identities here, and eventually you will still not get equal to 0. And I simplified this as 2 sine 2 theta cosine 2 theta plus sine squared theta. But you can obtain different answers depending on what identities you apply, or you can leave it as it is, and obviously it is not equal to 0, so they are linearly independent. Let's go to example 6. Our example 6 is more interesting because we're computing the determinant of 3 functions. So our Wronskian will be given by e to the 2t sine of 3t and cosine t as our first row. Our second row will be the derivatives of those functions. So 2e to the 2t, derivative of sine is cosine, times 3 is 3 cosine 3t. And derivative of cosine is negative sine. Again, we're going to take derivative again. Derivative of 2e to the 2t is 4e to the 2t. Derivative of this will be negative 9 sine of 3t. And derivative of this will be negative cosine t. Now we're going to set our determinant. Our determinant will be given by entry A, which is e to the 2t, times determinant of these entries. 3 cosine 3t, negative sine t, negative 9 sine of 3t, negative cosine t, minus entry B, which is sine of 3t, times determinant of 2e to the 2t, negative sine t, 4e to the 2t, negative cosine t, plus our last entry cosine t times determinant of 2e to the 2t, 4e to the 2t, and 3 cosine 3t, and negative 9 sine 3t. And when we're computing the determinant of those 2 by 2 matrices, we're going to multiply this entry by this entry, minus this entry by this entry. So multiply this entry by this entry, and subtract this entry times this entry. Similarly, we're going to multiply entry A and D and subtract entry C times entry B. So if we clean up, we obtain this. E to the 2t times negative 3 cosine squared of t minus 9 sine of t sine of 3t minus sine of 3t times negative 2 e to the 2t cosine t plus 4 e to the 2t sine t plus cosine t times negative 18 e to the 2t sine of 3t minus 2e to the 2t cosine of 3t. All we are doing is multiplying those entries times the determinant of these. And after this, if you distribute inside, and clean out, you obtain 15e to the 2t cosine t, cosine of 3t, minus 13e to the 2t sine t, sine of 3t, minus 16e to the 2t cosine t, sine of 3t as your final answer. So you can simplify this much. And this is not equal to 0, so those three functions are linearly independent. Let's go to our last example. Our last example is the Wronskian of t, t squared, and 2t cubed. So we can set our Wronskian as the matrix of t, t squared, 2t cubed. The first derivatives are 1, derivative of t is 1, derivative of t squared is 2t, derivative of 2t cubed is 6t squared. Let's take the derivative again. Derivative of 1 is 0, derivative of 2t is 2, derivative of 6t squared is 12t. Now our determinant will be given by t times this matrix. So t times the determinant of that matrix. T squared times minus t squared times the determinant of 1, 0, 6t squared, 12t matrix, and plus 2t cubed times determinant of 1, 0, 2t, 2 matrix. Now we can compute this. So t times determinant of this is 2t times 12t minus 2 times 6t squared. So 2t times 12t is 24t squared minus 2 times 6t squared will be 12t squared minus t squared times determinant of this matrix. 1 times 12t is 12t, 0 times that is 0, plus 2t cubed times t times 2 is 2t, minus 0 times 2t is 0. Now we're going to simplify this. 24t squared minus 12t squared is 12t squared. This is 12t, and this is 2t. T times 12t squared is 12t cubed, minus t squared times 12t is 12t cubed, plus 2t cubed times 2t is 4t to the 4th. Here, those two cancel out, so our answer is 4t to the 4th. And this is not equal to 0, so our functions are linearly independent because our Wronskian is not equal to 0. That's it for today's video. I hope you enjoyed. Here are the formulas for Wronskian, here how we take determinant, and those are the examples we did. If you have any questions, please comment below. Thank you very much.